Okay, Assalamualaikum and good morning, everyone.
Waalaikumsalam.
Morning, sir.
Okay, so last week we have learned about how to derive transfer function for translational mechanical system. So today we are going to look at how to derive the transfer function for rotational mechanical system. Okay, so after completing this lecture, you will be able to create transfer function for rotational mechanical system, for system without gearing, and also for system with gearing. Okay, so let's overview a bit about the difference between translational and rotational motion. So for a translational motion, it's a linear motion, meaning that the motion of a mass is either horizontal or vertical, while for rotational motion, it's a motion rotating about an axis. Okay, so each of this motion has its own spring and damper. So for translational and rotational motion, the spring and damper, the purpose are the same. Okay, but the shape or the design of the spring and damper are different. For example, for spring, for translational motion, uh, uses the one that I shown here. So it is a linear spring or a regular spring. Okay, but for rotational motion, the spring is slightly different. Okay, the design of the spring. So I think for rotational motion, you can find the spring, for example, in um, spit kain. Okay, peg. Okay, spit kain, spit baju. And for damper, usually we can find the damper that is attached to doors. Okay, if you go to supermarket, you can see this kind of damper attached to a door. But for rotational motion, the damper, I haven't seen one. Okay, probably you guys have seen this. Okay, but I never seen this kind of damper before. So for rotational motion, for rotational system, the modeling steps are the same. Okay, same with translational motion. So firstly, we need to decide the input and output, and then we need to list all of the forces by drawing the free body diagram, and then we need to convert the forces into frequency domain, and lastly, we need to find the transfer function. Okay, by isolating the input from output. And for each of the elements like spring, damper, and inertia, we need to first write the torque. So instead of force, we write torque. Okay. So for spring, the torque T equals the spring constant K times the angular displacement theta. For damper, the torque will be the damper constant times angular velocity d theta dt. And lastly, for inertia, the torque will be J times the angular acceleration, or d squared theta over dt squared. So similar to translational mechanics, for spring it's K times displacement, damper it's d times velocity, and inertia it's mass or J times acceleration. So when convert into frequency domain, uh, it is still the same thing. Okay, similar to translational motion. So for k theta in um, frequency domain, it will become k theta s. Okay, and for damper, it will become ds theta s. Okay, so ds because because it's the velocity. And then for inertia, it's J times S squared theta S. So S squared because it's acceleration, double differentiation. Okay. So let's look at an example of a rotational system without gearing. Okay, so figure here shows a rotational system that has three masses or three inertia, J1, J2, and J3. And here there is no gearing. Okay, so we look at a system without gearing first because it's the simplest thing that you can analyze. Okay, so here the arrangement is similar to translational mechanics. So we have damper, we have spring connecting uh, two masses. But here the difference is in terms of the degree of freedom. For example, theta 1 here, it measures the rotation, okay, measure the rotation of J1. Theta 2 measures the rotation of J2, and so on. So here the rotation is given clockwise. Okay, so if we want to draw the forces from damper and spring that is connected with J1, then the forces or the torque will be trying to resist the motion of theta 1, which means the forces or the torques will be in counterclockwise direction. Okay, so we will see later how to uh, draw the free body diagram and so on. So step one, we need to identify the input and output. So the input will be the torque T. So instead of force, here the input is the torque. So torque T here is applied on J1, okay, because it is before the spring, okay. So it's on J1, and then the output can be any of the theta, either theta 1, theta 2, theta 3, or the velocity or the acceleration. And then let's look at step 2 and 3, which is drawing the free body diagram and also writing the equation of motion. So let's look at J1 first. Okay. So instead of drawing a box, we draw a circle, okay, to represent its involved rotation. So here theta 1 is clockwise. So on J1 we have the inertia because it has mass J1 here. So we have one torque that is counterclockwise, J1 theta 1 double dot. And then on J1 we have one damper D1 and one spring K connected to J1. So we have to consider the force from D1 theta 1 dot and also K theta 1. So these forces are clockwise, are counterclockwise, okay, the torques. Then then we have the torque T. So the torque T is in the same direction with theta 1. Okay. And then the spring K here is also connected with theta 2. So we have the torque contribution from J2. So this torque will be clockwise. Okay. Or you can write similar to translational motion, you can also write K theta 1 minus theta 2 if you don't want to separate them. Okay. Then after you get this equation, this free body diagram, then you can write the equation of motions. Okay, now we look at the J2, the shaft J2. So for J2 we have the inertia J2 theta 2 double dot. Then we have a damper and a spring K and damper D2 connected with J2. So we have two torques in counterclockwise motion, counterclockwise direction. Then we have D2, the damper D2 connected with J3. So we have the torque contribution from J3. And then we have the spring connected with theta 1, with J1. So we have the torque contribution from theta 1. Then we can write the equation of motions. And lastly, for J3, so on J3, we have the inertia, and we have two dampers, D2 and D3, connected with J3. And then the damper D2 is connected with J2. So we have the contribution from J2. Then we can write the equation of motion. So we have three equations just now. Then we can convert them into frequency domain. So this is already converted into frequency domain. Then we can arrange them in matrix form. Okay, so make sure your matrix is symmetric. So if it is symmetric, then your answer is correct. Okay. Then let's say if we are interested to find theta 3, then we can use Cramer's rule. Okay, so find theta 3, just substitute the third column. So substitute the third column with the fourth column divided by the determinant of the original matrix. Okay, and then you can simplify the equation. Okay, usually I will simplify the top determinant. Okay, because the top one is easier to simplify compared to the bottom one. Okay, so because you want to find theta 3 over t. Okay, so you can try simplify the top one. Okay, so any question until here?
No, sir.
Okay, so I hope you already understand the similarity between translational mechanics and rotational mechanics without gearing. Okay, so the derivation process is similar. So um, I hope you can understand until this section. Okay, so now let's look at an example of what happens if we put gears into the rotational system. So firstly, what is gear? So gear is a tooth machine part such as wheel or cylinder that is meshed together with another tooth part to transmit motion or to change speed or direction. So if you look at this figure here, yang bergerak ni, so this gear is rotating counterclockwise. So the neighbor of this gear will be rotating in opposite direction. Okay, so when gear is connected to each other, so one rotate the other way around, the other one rotates in opposite direction. Okay, so we have normal gear, we have um, transverse gear. I forgot the name, and we have bevel gear here. So I think you have seen this probably in mechanical design. I'm not sure, but each of these basically uh, change the direction of motion and also can change the type of motion from rotation through to translation. For example, the bevel gear and the middle gear here, the translational gear. So before we can go into detail about deriving system with gears, we need to understand the properties of gear. So the two gears turn in opposite direction. So as I said just now, if one gear rotate clockwise, then the neighboring gear will rotate counterclockwise. Then two gears revolve at different speed depending on the number of teeth on each gear. Okay, so usually bigger gear will rotate slower, okay, compared to smaller gear. Yeah, okay. Later we'll see the formula. I forgot. Okay, so we have the concept of gearing up and gearing down, similar to when driving your car. So I think automotive student understand gear better than everyone in this class. Okay. So gearing up is able to convert torque to velocity. So if you gear up, uh, velocity increases. Okay. So the more velocity gain, meaning that you sacrifice torque. Okay. So if you gear up, if you go to gear 5 when driving, you can increase your speed, but the torque is less. Okay. Less torque for higher gear. So the ratio is exactly the same. If you get 3 times your original angular velocity, then you reduce your torque 3 times. So the conversion is symmetric. So we can convert velocity to torque at the same ratio. So when converting this, we have power loss. Okay, so power loss in this topic, in this subject, we consider no power loss. Okay, no friction between the gears. But sometimes we have friction, but we will look at it later in tutorial. Okay. So for example, here in this figure, we have one gear has 8 teeth and the other one has 24. So the gear ratio is 3 to 1. Okay. So gear ratio is 24 divided by 8. Okay. 3 to 1 ratio. So if we turn the smaller gear 3 times, then the bigger gear will complete one cycle. Okay. So 3 cycle for one smaller gear here will cause the bigger gear to complete one cycle. Macam putaran bumi, bulan dan matahari. Okay, so it depends on the number of teeth. Okay, so why we need gearing? So a typical DC motor. So maybe if some of you are designing IDP project involving DC motor, so when designing DC motor involving DC motor, DC motor usually has a smaller torque, okay, but a very fast speed. So we need to reduce the speed and increase the torque, okay, so that it can rotate bigger components, okay. So that's why we need gears. So we apply gears onto the DC motor so that it can turn uh, bigger or heavier load. So we can calculate the gear ratio by using the number of teeth of driver divided by the number of teeth of follower. Okay, so the driver and follower is depends on how which one you define. Okay, so if you define the smaller gear as driver, then the gear ratio is 1/3. Okay, so if you define the smaller gear as the follower, then the gear ratio is 3 to 1. Okay, so it depends on which one is your follower, which one is your driver. Okay, so we can gear up. So gear up, increase the velocity, decrease the torque. Okay, so gear up, basically the gear ratio is from bigger gear to smaller gear. So gear down, we increase the torque but reduce the velocity. So from smaller gear to bigger gear. So gear ratio is the number of teeth from input gear divided by number of teeth of output gear. Or we can write n input divided by n output. So this is also equals to torque input divided by torque output, and also equals the speed speed output divided by speed input. Okay, so this is the first formula that you need to understand. Okay, so gears increase or reduce angular velocity. So this is just derivation. Later on we will see which formula to use. Okay, so by using the conservation of energy, so energy from driving gear equals the energy of following gear. So energy equals number of teeth times the displacement, the angular displacement. So n1 times theta1 equals n2 times theta2. Okay, so this is this formula you need to remember. Okay. Then considering the angular displacement or the circumference traveled by each gear, so uh, the circumference for gear 1 will be similar to circumference of gear 2. Okay, the circumference traveled. Okay, the distance traveled. So S1 equals S2. So R1 times theta1 equals R2 times theta2. Then rearrange. So ratio of radius between gear 1 and gear 2 is equal to the number of teeth between gear 1 and gear 2. Okay. So this is back to the previous formula, okay, using conservation of energy. So N1 over N2 equals theta2 over theta1. Or you can write in terms of transfer function. Okay, so let's say your input is theta1, your output is theta2, then the relationship is N1 over N2. Oh, dah ada. Okay, so here we use the concept of work or energy. So work also equals the torque times displacement, okay, angular displacement. So T1 times theta1 equals T2 times theta2. So we can rearrange this. We get T1 over T2 equals theta2 over theta1. But theta2 over theta1 also equals N1 over N2. Okay, so this formula is important for calculating gear ratio. Okay, so T1 over T2 equals theta2 over theta1 equals N1 over N2. Okay, so let's look at the application of gear ratio with the rotational system. Okay, so let's say you are given a system with 1 degree of freedom. Okay, so here we have a shaft that is connected with gear N1. Okay, so here the garisan here represent gears. Okay, okay, so we have this gear. The number of teeth is N1, and then on this shaft, the rotation, the angular displacement is theta1, and then it is supplied by a torque T1. Okay, And then the gear N1 is connected with gear N2. So the number of teeth is N2. And then in this shaft here, we have rotation angular displacement theta 2. And then we have an inertia or mass J connected with a damper and spring to a wall. Okay. So if we fix J, let's say if we hold this J here, pegang dia, jangan bagi dia gerak, then the system will be unable to move. Any part of this system will not move, okay? Because when you hold J, then gear N2 will be fixed as well, okay? So when gear N2 is fixed, then gear N1 cannot move, okay? Because they are connected together. So because of that, because when you fix only J, then everything will not move, then the system has only 1 degree of freedom. So we can use the same modeling step using the one that you have learned just now, the system without gearing. Okay, so step 1 is we need to identify the input. So the input is the torque, and then the output can be theta 1 or can be theta 2, okay, depending on which one you want to measure, okay. Then step 2 and 3, we need to draw the free body diagram and write the equation of motion. So firstly, let's write the relationship for gears. Okay, and then we can convert this gearing part using this relationship. Okay, so what this figure did was from this theta 1, it tries to relate theta 1 to theta 2. Okay, so theta 1, if you multiply with this gear ratio, becomes theta 2. Okay, so using this formula, so theta 1 times n1 over n2, you get theta 2. Okay, so you just write theta 2 here, or you can write in terms of theta 1. Theta 2 equals theta 1 times n1 over n2. Then we bring this torque T1 here to the other side. Okay, so to bring T1, you just multiply. You assume, okay, you assume this torque here is T2. So to get T2, you just bring using this formula here. Okay, so T2 equals N2 over N1 times T1. Okay, so that's why here the figure is redrawn. So you redraw the figure to remove the gear. So you get T1 times N2 over N1, which is equals T2. So now we remove this section N1 here by converting T1 into T2 and theta 1 into theta 2 by multiplying the gear ratio. Okay, so when you multiply the gear ratio, then you can remove the gearing part. So here the system has no more gear already because you have considered the gear ratio. So this system here is similar to the one without gearing, the system without gearing. So you can draw the free body diagram. So here theta 2 is counterclockwise, sorry. Then we have the inertia from J. So J theta 2 double dot will be clockwise. And then the damper and also the spring. All of these are clockwise. Then we also have the torque. which we have convert. Okay, so we use T2. So T2 equals T1 times N2 over N1. Okay, so we have all of the forces here. Then you can write the equation of motion. And then convert into frequency domain. Then we can rearrange this. So we get theta 2 over T1. You get this transfer function. Then we can also, from this we get theta 2. So we can find theta 1 by using the gear relationship, okay, the gear system relationship. So theta 2, if you want to find in terms of theta 1, so you just substitute theta 2 equals theta 1 times N1 over N2. So here is the equation for theta 2. Then you just substitute theta 1. Then you can rewrite the transfer function in terms of theta 1. Okay, so you have transfer function in terms of theta 2 and also in terms of theta 1. Okay, so this is the transfer function from theta 1. So here we have this equation of transfer function. We have N1 over N2 squared for each of the inertia J, damper, and spring K. So here, the gearing system causes some impedance transfer. So we call this N1 over N2 squared as impedance transfer. So to find the impedance transfer, basically we use this relationship. K destination equals K source times N destination over N source squared. Okay, so we will look at this later. What is this and how to use this? Okay, so this is the original figure, okay, from the problem just now. Okay, so here we can see that all the spring, damper, and inertia J are located on the shaft with theta 2. But in theta 1, in shaft with theta 1, there is no spring, damper, or J inertia. So, but the equation, the transfer function theta 1 over T1, in the transfer function, there is the term J, D, and K. So J, D, and K actually comes from theta 2, okay? So basically, this impedance, J, D, and K, are transferred from theta 2 to theta 1. Okay, so as I said, the impedance are transferred from theta 2 to theta 1, okay? But to transfer this K, for example, K, you have to multiply with N1 over N2 squared. So how to determine what to multiply, y N1 over N2? So to do this, you need to identify which one is the destination, which shaft is the destination, and which shaft is the source. Okay, so source is the location where you have the spring, damper, and inertia that you want to transfer. So here in theta 2, we have the J, damper, and spring that we want to transfer to theta 1. So here, theta 2 is the source, okay? So the shaft consists of theta 2 here is the source. And then the shaft with theta 1 is the destination. So you just substitute here. K source is the K here. N destination is this N1. And then N source is the n on the source, which is n2. So that's why you get in the k for theta 1 or k destination equals k times n1 over n2 squared. Okay, so let's look at the damper pula. Okay, using the same formula, so to get this n1 over n2 squared times d, so here we have damper d from theta 2. So theta 2 is the source, okay, and theta 1 is the destination. So to get d on the destination, you use this. K source is d times n destination is n1, sorry, n1 divided by n source. So n source is n2 squared. Okay, so here is your d destination or d theta 1. Okay, so you get this value here. And then similar to the inertia. So inertia is located on theta 2. So we need to apply the uh, impedance transfer formula. So what is this example show actually is you can find theta 1 over T1 without doing the free body diagram, the steps. Okay, the steps from identifying input output until calculating the transfer function. You can just use this concept, just transfer the impedance. Okay, and later we will see an example maybe this Wednesday. Okay, so let's look another example at another example. So here we have T1 and theta 1 located on this shaft. So now this shaft has J1, mass J1, and also damper D1. So compared to previous example, we have nothing on theta 1. But now on theta 1, we have J1 and D1. On theta 2, we have the same thing. We have J, damper, and spring. J2, D2, and K2. So the difference here is we have J1 and D1 on theta 1. So we can perform impedance transfer, okay? So how to find transfer function, let's say theta 1 over T1 or theta 2 over T1, okay, whichever, okay. So first we need to perform impedance transfer. Okay, so the question asks you to find theta 2 over T1, okay. So if you want to find theta 2, meaning that you have to transfer everything from theta 1 to shaft theta 2. If you want to find theta 1, then you transfer everything from theta 2 to theta 1 or vice versa, okay? So let's look at this example. So we want to find theta 2, okay? So if you want to find theta 2, basically you have to transfer everything from theta 1 to shaft theta 2. So meaning that you're transferring from source to destination. So theta 1 here, you can identify this as the source. And then the whole shaft on theta 2, you can identify it as the destination because you're transferring from theta 1 to theta 2. Okay, so we transfer each of the components one by one. Okay, so now we transfer D1 first to, we transfer D1 to shaft theta 2. Okay, so on theta 2, we already have D2. So we need to find the um, equivalent damper. Okay, so how to find equivalent damper? Firstly, we have D2 in shaft J2 in shaft theta 2. So we have D1 from theta 1. So we apply impedance transfer. So here we just add, okay, we just add D2 and also the impedance transfer from D1. So we have D2 plus D1 times N destination, which is N2, divided by N1 or N source, which is N1 squared. Okay. Okay, so we use N2 because N2 is the destination, is on the destination. Okay, now we transfer J. So we transfer J1 into the second shaft or shaft theta 2. So we get the J equivalent equals J2. So we already have J2 here plus J1 times N2 over N1 squared. So similar to damper. Okay. Now on this shaft, theta 1, we have no spring, okay, on theta 1. But on theta 2, we only have we have spring K2. So the equivalent spring, the K equivalent, equals only K2 because we don't have spring from theta 1. So we don't transfer any impedance from the spring. So the spring equivalent equals only K2 plus nothing. Okay. So we have transferred everything just now from D1, J1, and the spring. So we transferred D1, we get the D equivalent. We transfer J1, then we get J equivalent. And we don't transfer spring because there is no spring from theta 1. So the K equivalent is equals K2. So we only transfer the remaining torque and also theta 1. So theta 1 basically you don't have to transfer because on shaft theta 2 we already have theta 2 here. So we can just represent the rotation by theta 2, and the torque, you transfer the torque equals T1 times N2 over N1. So remember, only impedance, you need to square the gear ratio. But for the torque or for the angular displacement, you don't have to square, okay, power 2, only the impedance. So after you transfer everything, then you can draw the free body diagram. Okay, so draw the free body diagram based on this J equivalent here. And then you can write the equation of motions in terms of frequency. Then you can substitute J equivalent, D equivalent, and K equivalent from the formula that you have calculated. Then rearrange, you get theta 2 over T1, okay? You can rearrange by yourself later. And if you want to find theta 1, you just use the gear ratio and substitute into theta 2. Okay, so that's it, okay, for today. Any question?
No, sir. So far, no.
Okay, so for this chapter, you need to understand how to transfer the impedance. Okay, so that's the most important. So before you can transfer impedance, you need to identify which one is your source and which one is your destination before you can perform the transfer. Then uh, after you transfer everything, then you can redraw the free body diagram, redraw the system, and draw the free body diagram and write the equation of motion. Maybe you don't understand now, but on Wednesday we will look at some of the tutorials, and perhaps when doing the tutorial you will understand more. So maybe you can try doing the tutorial by yourself first, then on Wednesday you can check with my answer. So if you have no more question, that's it for today's class. See you again inshallah on Wednesday. Thank you very much. Assalamualaikum. Bye.
Thank you, sir.
Thank
Thank
you.
you.
Thank you, sir.
Thank you, sir.